Marine plastic is a relatively new challenge that we face, but we're treating it with very old methods. People in boats fishing out plastic all day long.
The majority of plastic in the ocean comes from rivers, around 4.7 million kilograms every day. If nothing changes, ocean plastic pollution will quadruple by 2050.
America's ocean cleanup machines are not simple nets or floating barriers. They are far more advanced, powerful, and far more strategic than most people realize. While the world struggles with billions of tons of plastic choking the seas, the United States has been developing autonomous cleanup systems that move, react, and capture waste with surprising precision. These machines do more than skim the surface. They track currents, adapt to changing conditions, and convert recovered debris into new resources. The real story behind them is far more impressive than anyone expected, and it all began with an ocean crisis. The ocean crisis. No one can ignore. The oceans are not just polluted, they are being suffocated. A silent and deadly flood of plastic is spreading through the water every single day, far from beaches and far from human eyes. Each year, close to 20 million tons of waste are pushed into the world's seas, and almost 80% of that waste is plastic. This disaster does not arrive with noise or warning. It slips into the water quietly and never leaves. What begins as bottles, bags, and broken tools quickly becomes something far worse. This plastic does not stay on the surface where it can be easily seen. Some pieces float for a short time before sinking into deep and dark waters. Other fragments stay suspended in the middle of the ocean, drifting with slow currents. Over time, sunlight and waves tear the plastic apart into tiny pieces called microplastics. These pieces are so small that the human eye cannot see them, yet they remain deadly. They do not disappear. They linger for centuries, spreading through every layer of the ocean. These tiny fragments move straight into living bodies. Fish swallow them without knowing. Plankton absorbs them. Larger animals eat smaller ones, and the plastic moves upward through the food chain. Entire marine ecosystems are being poisoned from the inside. This damage is not sudden. It builds slowly, day after day, until whole systems begin to collapse. Powerful ocean currents make the problem even worse. Massive circular currents, known as gyres, pull debris into tight spirals and trap it there. Over time, these areas become huge collection zones for plastic waste. The most infamous of these is the North Pacific Garbage Patch. It covers an area larger than the state of Texas, and it is packed with bottles, fishing nets, ropes, food wrappers, and broken plastic parts from decades of human use. This floating mass is not just ugly to look at, it is a killing field. More than 700 marine species are affected by plastic pollution. Some animals choke when they try to swallow it. Others become tangled in nets and lines that never break down. They struggle, weaken, and die slowly. Turtles are trapped underwater and cannot reach the surface to breathe. Birds fill their stomachs with plastic fragments and starve because there is no real food inside them. The damage does not stay in the ocean. It comes back to humans. Microplastics now exist in seafood that people eat every day. These particles carry chemicals and toxins that were never meant to enter the human body. Scientists are still trying to understand the full risk, but the warning signs are already clear. The ocean itself makes cleanup even harder. It is unpredictable and dangerous. Calm surfaces hide strong currents below. Storms scatter debris across thousands of miles. Fishing nets drift like invisible traps. Plastic waste moves silently with the tides. Marine animals never see the danger until it is already killing them. Most of this destruction happens far from shore, where no one is watching. Traditional cleanup efforts cannot keep pace with this crisis. Nets used for cleanup can trap animals instead. Fixed barriers break or fail when storms hit. Human crews can only work for short periods and only in safe conditions. The ocean is simply too vast, too deep, and too powerful for these methods to succeed. This reality forced a different way of thinking. American engineers realized they could not fight the ocean head-on. Instead, they chose to study how it moves and learn how to use that movement itself as a weapon against plastic pollution. How America's intelligent ocean collectors captured debris. The advanced machines built by American engineers are not passive tools drifting helplessly at sea. They are designed to think, react, and adapt in real time. These autonomous ocean collectors do not anchor themselves to one location like many foreign systems that fail when conditions change. They move with intention. They travel where the ocean moves and position themselves where pollution is most likely to gather. This decision alone changes everything. Each collector is packed with advanced sensors that never stop working. They constantly measure water speed, current direction, wind force, wave height, and the density of debris in the surrounding area. All of this information is sent to onboard software that analyzes the data second by second. The system identifies natural convergence zones where trash is pushed together by currents. Instead of chasing plastic across open water, the collectors wait in these zones and let the ocean deliver the waste directly to them. When storms form or tides shift suddenly, the machines react instantly and move out of danger. They reposition themselves without human command and continue operating through day and night without rest. When debris builds up beyond capacity, support vessels are sent in. These ships are not small cleanup boats. They are heavy-duty platforms designed for extraction. Each vessel is fitted with massive hydraulic arms that sweep across wide sections of water. The arms move slowly to avoid harming marine life, but their force is relentless. Floating waste is pushed into controlled channels where nothing escapes. Conveyor systems lift the debris onto the deck and seal it inside secure storage compartments. Nets, ropes, bottles, crates, and shattered plastic parts stack up fast. In a single work shift, entire fields of debris are removed. This is not cosmetic cleanup. This is industrial-scale removal. Closer to shore, the fight becomes even more brutal. Rivers and canals act like funnels, trapping trash and crushing it into thick layers. Here, truck-mounted clamshell excavators tear into compacted waste. Each scoop drags up massive loads filled with plastic, tires, and rotting debris. In shallow waters, volunteers and fishermen step in where machines cannot reach. Their knowledge of local currents and hidden buildup zones makes the operation faster and more precise. This system succeeds because nothing operates alone. Automation, hydraulics, artificial intelligence, and human judgment work together as one unit. Engineers constantly update algorithms as drift patterns change with seasons and weather. Every move is calculated. Every adjustment has a reason. This is a controlled assault on a moving and unpredictable enemy. But removing plastic from the water is only the first step. To finish the job, everything collected must be sorted, cleaned, and recycled before it can truly be removed from the cycle of destruction. From sea to shore, sorting and cleaning the ocean's plastic. When the debris finally reaches land, the damage can no longer be denied or ignored. What arrives is not a pile of clean trash. It is a massive, tangled, foul-smelling mass that looks more like a wreckage site than waste. Plastic is fused together with splintered wood, twisted metal, fishing gear, shells, and thick sea growth. Everything is soaked in salt water. Every surface is slimy. Bacteria thrive in the moisture and decay. At this stage, none of this material can be recycled. It is both a biological threat and a mechanical danger. The first step is survival. Safety teams move in before processing begins. Large and dangerous items are pulled out immediately. Steel fishing nets are under tension and can snap back without warning. Oil drums may still contain toxic residue that leaks when disturbed. Tires and heavy metal objects can crush equipment or injure workers. Removing these threats is slow and careful work, but it is essential. Only after the most dangerous items are cleared can real processing begin. Even then, the volume is crushing. Mountains of bottles, food packaging, shattered containers, and unidentifiable plastic fragments remain locked together by algae, slime, and hardened residue. Nothing is separated, nothing is clean. This is where sorting begins. The first sorting stage uses massive rotating trommel drums. These machines are large steel cylinders that spin continuously. As the waste moves through them, material is separated by size. Sand, silt, and fine particles fall through openings and are removed from the flow. What exits the drums is still chaotic and unstable, but it is manageable enough for human hands. Workers step in next because machines alone cannot make the necessary judgments. They manually separate plastic from wood, metal, and glass. They also identify specific plastic types such as PET and HDPE. This step is critical. Mixing plastic types weakens anything made from them later. A single wrong item can contaminate thousands of pounds of material and ruin an entire batch. Once sorting is complete, cleaning begins, and this stage shows no mercy. Mechanical paddles scrape and grind away hardened growth and residue. Powerful washing systems flood the plastic with water and cleaning agents that strip away salt, grease, and organic matter. Some facilities use heated water or ozone treatment to kill bacteria and destroy the foul odors trapped inside the material. Nothing is rushed. If contamination survives this stage, it will destroy everything that follows. After washing, plastics are separated again based on density. Heavy plastics sink while lighter plastics float, allowing precise grouping. Moisture is then removed using centrifugal dryers and hot air systems. Dry material is essential for controlled processing. By the end of this stage, the transformation is shocking. What arrived as a toxic and dangerous mass is now clean, dry, and stable. This process does not create value yet. It creates control. It turns chaos into order and prepares the material for the precision work that comes next, ensuring that destruction does not continue further down the line. Advanced sorting and granulation, turning waste into uniform material. Once the plastic has been cleaned and fully dried, it enters the most controlled and unforgiving phase so far. There is no room for error here. High-speed optical sorting systems take over, and human hands step back. Every single plastic flake moves along conveyor lines at extreme speed. In a fraction of a second, sensors scan each piece. They identify its chemical structure, its color, and any sign of foreign material. This happens almost instantly and without pause. The moment something does not belong, the system reacts. Compressed air jets fire with exact precision and blast the contaminant out of the moving stream. These bursts happen thousands of times every second. The machines never slow down and never get tired. No human team could match this level of speed or accuracy. This stage acts as a final gate. Only approved material is allowed to continue. Everything else is removed before it can cause damage. What remains is a tightly controlled flow of uniform plastic. Every flake now meets strict standards. This precision is not optional. The machines that come next cannot handle variation. Even small inconsistencies can break equipment, waste energy, or ruin entire batches. Uniform input protects the system and locks in predictable results. The plastic then moves into granulation. This is where size and structure are forced into complete control. High-speed granulators tear the material apart using rows of hardened spinning blades. Bottles, containers, and fragments are shredded into standardized flakes. The noise is relentless and heavy. These machines process enormous volumes every hour without stopping. Engineers monitor blade speed, pressure, and output constantly. If flakes are too large, they will jam downstream systems. If they are too small, they will degrade during heating and lose strength. Granulation serves several purposes at once. It reduces bulk. It creates uniformity. It prepares the material for precise heating later. This is also the moment when the transformation becomes impossible to deny. The plastic is no longer treated as waste. It is now a controlled industrial input. Power consumption is tracked in real time to prevent unnecessary loss. Adjustments are made continuously to keep output stable and efficient. By the end of this stage, the change is absolute. Material that once spread disease, trapped animals, and poisoned ecosystems has been stripped of chaos. It now exists as clean, uniform plastic flakes, ready to enter the next phase of industrial processing. Pelletization, transforming ocean waste into industrial feedstock. During the pelletization stage, the flakes are fed into massive extruders and heated to approximately 520 degrees Fahrenheit. At this temperature, the plastic becomes molten and viscous, resembling a thick, flowing liquid. A powerful rotating screw pushes the molten material through a series of metal screens that capture remaining impurities, such as sand, small rocks, or leftover organic debris. This filtration ensures that the final material is clean and ready for further processing. This stage requires careful control of temperature, pressure, and speed to prevent degradation of the plastic, which could reduce the quality of the end product. After passing through the screens, the molten plastic enters an underwater pelletizer. High-speed blades cut the flowing material into uniform, small pellets. These pellets are immediately cooled in a closed-loop system, solidifying them with consistent size, density, and surface finish. This cooling step is crucial. Without it, the pellets could stick together or deform, compromising downstream production. Each pellet is now a compact, reliable industrial feedstock ready for packaging, textiles, or bottle manufacturing. Recycling at this scale offers significant environmental benefits. The process reduces reliance on virgin plastics, lowers energy consumption by up to 40%, and significantly reduces CO2 emissions compared with producing new plastic from petroleum. Quality control is central to every stage. Each batch of pellets is carefully monitored for size, density, and purity. This ensures that when the pellets move on to the molding phase, they meet the high standards required for safe, functional consumer products. The pelletization stage is more than a mechanical operation. It is the bridge between ocean waste and sustainable manufacturing. By turning discarded plastic into standardized, industrial-grade pellets, this process gives new life to materials that would otherwise pollute the environment. Each pellet is tested for size, density, and purity. Only approved material moves forward. At this point, the ocean waste is no longer debris. It is industrial feedstock, ready to move to molding facilities where its next transformation begins. Once the flakes are prepared, they are moved into the most intense phase of transformation so far, They are fed into massive industrial extruders built to handle extreme heat and pressure without failure. Inside these machines, the plastic is heated to around 520 degrees Fahrenheit. At this temperature, the solid flakes lose their shape completely. They soften, melt, and turn into a thick, slow-moving liquid. This molten plastic is heavy, sticky, and unstable if not handled correctly. A powerful rotating screw inside the extruder forces the molten plastic forward in a controlled flow. As it moves, it is pushed through layers of fine metal screens. These screens act as a final defense. They trap anything that should not be there, including sand, tiny stones, and traces of organic debris that survived earlier stages. Even the smallest impurity can weaken future products, so nothing is allowed to pass unnoticed. Engineers monitor temperature, pressure, and flow speed constantly. If the plastic overheats, it begins to break down and lose strength. If it cools too quickly, it thickens and causes dangerous pressure buildup. Every variable must stay within strict limits. After filtration, the molten plastic flows directly into an underwater pelletizer. This machine works at brutal speed. Sharp blades slice the flowing plastic into small uniform pieces the instant it exits the extruder. These pieces drop immediately into circulating water that cools them on contact. This rapid cooling locks in their shape and strength. Without this step, the pellets would stick together, deform, or collapse under their own heat. The cooling system is closed and controlled. Water temperature, flow rate, and circulation are constantly adjusted to maintain consistency. The result is pellets with identical size, density, and surface quality. Each one is a compact unit of controlled material, ready for industrial use in packaging, textiles, and bottle production. This process delivers real environmental impact. Recycling plastic at this scale reduces the need for new plastic made from oil. It cuts energy use by up to 40% and sharply lowers carbon emissions compared to producing new material. Quality control never stops. Each batch of pellets is tested repeatedly for size, density, and purity. Anything that fails is removed immediately. This stage is more than mechanical work. It is the final crossing point. What once poisoned the ocean has been stripped of danger and chaos. At this point, the waste is no longer waste. It is industrial feedstock, ready to move to molding facilities where its next transformation begins. From pellets to bottles, the art of preform and blow molding. Pellets may look harmless, but turning them into bottles is a high-pressure operation where precision decides success or failure. The next phase begins inside injection molding machines that operate non-stop. Thousands of pellets are fed into heated chambers where they melt again under controlled force. This is not simple melting. The plastic must reach the exact state where it flows perfectly without breaking down. The molten plastic is injected into steel molds with extreme pressure. These molds shape the material into preforms. A preform is small, thick, and deceptively simple. It must survive reheating, stretching, and sudden expansion without cracking. Every millimeter matters. Engineers design these shapes carefully because the final bottle depends entirely on how this stage is executed. Sensors track temperature and pressure during every injection. If air gets trapped, the preform is rejected. If thickness varies, it is rejected. There is no tolerance for weakness. Once formed, the preforms are cooled and inspected before being packed for transport. Thousands can be stacked tightly and moved efficiently to bottling plants. At the bottling facility, the pressure rises again. Preforms are fed into reheating ovens where they become flexible, but not molten. Timing here is critical. Too much heat causes sagging. Too little heat causes tearing during expansion. Each heated preform is placed into a mold shaped like the final bottle. High-pressure air blasts into the preform, forcing it to stretch violently outward. The plastic expands 4 to 5 times its original size in seconds. This moment defines the bottle. Wall thickness, clarity, and strength are set instantly. Laser inspection systems scan every bottle the moment it exits the mold. They catch flaws invisible to the human eye. Any bottle that fails is removed immediately. Cooling follows fast. Chilled air or water locks the shape in place. Some systems capture excess heat to reduce energy waste. At the end of this stage, recycled plastic has become a finished bottle that meets strict performance standards and is ready for final testing. Quality control, distribution, and the circular economy impact. Even after bottles are formed, the danger is not over. Weaknesses can still hide beneath smooth surfaces. This is why quality control is relentless. Bottles move through inspection lines filled with cameras, sensors, and pressure testers. These systems work at high speed, checking every surface for cracks, bubbles, and thin spots that could cause failure during filling or transport. Some bottles are pulled from the line for destructive testing. These bottles are crushed, stretched, and slammed with force. If they fail, production stops and adjustments are made immediately. This constant testing ensures that problems never reach consumers. Chemical safety checks confirm that the plastic is safe for food and drink contact. Nothing moves forward without approval. Once cleared, bottles are transferred to automated palletizing systems. Robotic arms stack them with precision that humans cannot match. Every movement is calculated to prevent damage. Labels are applied to track each batch from recycled source to final destination. This traceability allows rapid response if issues arise later. Distribution then begins. Bottles move to filling plants, warehouses, and retail supply chains. Efficient logistics reduce fuel use and emissions while keeping timelines tight. Every step is measured and monitored. This entire system proves the power of a circular economy. Plastic that once drifted in the ocean now re-enters society as a useful product. Energy use is lower than producing new plastic. Emissions are reduced, waste is minimized. From ocean recovery to pelletization, molding, testing, and distribution, every stage is connected. Nothing is accidental. This process shows that pollution does not have to be permanent. With control, discipline, and engineering, waste can be forced into usefulness and returned to the economy as a valuable resource.